Right, let's now move into the programming part. So firstly, let me show you how we can build a new Rust project using the cargo toolkit. So we firstly just type in the cargo new command with the name that you like. So maybe it's demo. Then a new folder will be created for you. You can check out through the list command. Then let's get into the demo project folder and then see the files and the project structures. As introduced, source is where you store your source code, and let's get in there. Then we can see your main.is is created for you, so you can start editing it using vim main.is. And this is the code that was created for you as a template, so we can just start program from here. Now let's get into the first concept in Rust, the ownership. Say we have an object called craft string, and it has an owner, which is the underscore s. Underscore is just a naming convention for the variables that will only be used in this specific inner scope. So please ignore the underscore for now. It's just a name. So we have s as the owner of the craft string. And in Rust, when an owner gets off the scope, you'll be freed and the memory allocated to it will be released by Rust. So we have defined the drop function for the object craft string. So what drop function does is simply will be called when the craft string is being destroyed. So from this program, what we expect to see is that it firstly prints out the program started, and then it enters a scope. Then the craft string is initialized and is assigned to s, and then we should say that we should see that the s is going to be dropped because it's running out of the scope. So you should be able to see that theoretically. And then you see the program ended is being printed. So let's see what will happen actually. So let's go back to the command line and do cargo run. Here you go. So we see program started, and my name is varies, which was the string we defined in the program, and it's being destroyed. Well, it ran out of the scope, and then program ended. So we have seen everything expected. So that's basically how ownership works. Now let's look at a simpler concept in Rust, the immutability. So all variables are default immutable in Rust, unless you explicitly define them as mutable using the mute keyword. Say we have this program, you define a with an initial value of 1 and you print it out, and then you try to change it to 2 and then print it out again. So you will encounter errors with this code because a is immutable by default. Let's see that in action. So if you do a run, you will see errors. You cannot assign twice to immutable variable. So how we fix it? We just follow the instruction given by the Rust compiler. We just add a mute keyword here. Then it sure works. Oops, sorry. Then let's do the cargo run again. Hooray, it runs, right? Now let me introduce the move, copy, and clone to you in Rust. So some types like string will be moved if it's assigned to a new value. Say in this program, we have a is initialized with a string of hi, and it is then assigned to b. So this is where a is moved to b. When I say move, it means the transfer of ownership. So the string of hi is transferred to the owner of b, and a is then becoming invalid. So if you run the program now, you will see errors. Let's just do that. Oops, sorry. And yeah, we see the error, the value borrowed here after move. So that's where I said the move was. So how do we fix that? We use a clone. So clone is essentially a deep copy of the data. So we have, rather than move the data, we just deep copy it. So let's do a.long. And now if you run it again, the error should just disappear. Yes. So we still have the linter warning saying that it's not a great naming convention. You should follow that. But that's not really the concept of this example. You do not have to wait until a value goes off its scope to release it. You can always try release it earlier using the memory method drop to release it from memory earlier. Now let's look at the references and the borrowing. So there are three simple rules in Rust for this kind of mechanism. So you can only have one mutable reference. And the second is that you can have multiple immutable references. And the third is that you cannot mix mutable reference with immutable references at the same time. So in this code, these two lines where I'm highlighting are fine because they're just immutable references and they cannot make change to the data they refer to. But the third line is not okay because it is a mutable reference and it can change the values through the references. And we are essentially just mixing the use of mutable references and the immutable references. So what will happen if we run this code? We will surely get an error, but let's see what that error is. So we see that we cannot borrow I as mutable because it is also borrowed as immutable, right? That match the third row I've just told you earlier. Then let's edit the code again to see what we can do else. If we do have, for example, another mutable reference here, say we have f equal another mutable reference I. And let's see what happens. Let's change this. F equals second mutable borrow. So the multiple mutable reference are not allowed. So that's pretty much the problem with that. The idea behind these rules are that, say, for example, if you have two mutable references, that means you both can edit the value you refer to at the same time, and this would cause data race. So you do not want to try changing the code, changing the value in runtime at the same time, right? So that's pretty much a smart design with regarding to avoiding synchronizing problems. Right. Let me now introduce some more exciting concept of multi-threading. Do you still remember that the example I told you about two crabs are able to grade to you at the same time if you use thread? So here is an example of that. We have crab 1 as a thread that say hello from crab 1, and we'll have crab 2 as another grading thread saying hello from crab 2, and we then join the main thread of the program. So that's the running program behind. Let's see what happens. So we basically can say that to crabs saying hello to you, but because they are printing out in series, so they're meant to be running, kind of simultaneously because they are doing, their works on their own. And that's a very basic example of, multi-threading. You can implement much more complex tasks using multi-threading. I think one of the good examples to be included is that, say, for example, you are designing a mobile app that would download something at the backend. If you implement the downloading task in the same thread where you render your UI, then your user interface will just be frozen and will be frozen until your download task is finished and go back to the rendering task. So with the multi-threading, you can do your downloading work in the background thread while not affecting the front-end UI rendering thread at all. So multi-threading is really something useful in the modern programming world and operating systems. So it's a good concept. Now let me introduce a slightly more challenging topic to you, the closure. You still remember the Ferris and his grandchildren example I made you in the instruction tutorial videos? So we will just implement that for the demonstration of closure. So for example, Ferris has a recipe and ingredients of apple pie, and the ingredients are just apple and pie. And we have a closure. So from this line, so from when highlighting to this is the box where Ferris can store its recipe and ingredients. So it's basically just doing a printing, but just imagine that it is a box that will show what's inside. So we have Ferris recipe and ingredients, and we just put them in the box here. In the box here with the recipe and ingredient data. See, a few hundred years later, after a long time of this closure being created, the grandchildren of Ferris found this box and they want to see what's inside. And by having this thing written as a closure, the grandchildren can still find what Ferris put in the box, i.e., the closure at the beginning. So if we run the Ferris recipe now, you will see that its recipe and ingredient that Ferris put in the box at the beginning will be carried to here as well. Let's run it. Here you go. We can see the recipe of apple pie and apple and a pie, which was the recipe and ingredient Ferris put in the box, the closure at the beginning. So the core idea behind the closure is that it can carry logics and data around it, and to be used later in the code. Now let's get a bit deeper in the multi-threading in Rust. So let's look at how different threads communicate with each other. So in Rust, we use a type of channel called MPSC channel. So MPSC stands for multiple producers and single consumer, basically. We want to send something to another thread. What do is you send the data using the interface provided by the MPSC, and you can then receive your sent message in the target thread by using the RX, the receiver method, RECV. So once you finished receiving it, normally if you just read the code like that, it wouldn't work because the main thread would finish before the another thread you just created finished. So we have to let the another thread finish first. So we use another thread to join and to do that. So let's look at how it runs. We go cargo run and we can see that the data that was sent by the main thread has already been successfully received by the another thread we created. So that's for the thread communication. Now let's look at by far the most challenging topic in today's exercise. So basically, we want to handle a stinging event, that is the Ctrl+C event sent by the user, and we want to notify other thread that we get this event, but we want to not block the current main thread that we're running. So we want to send the message to other thread using a new thread other than the main thread, and we want to receive the message from the third thread. So it seems to be a little bit complicated, but it's not really. Let's look at the code for now. So first of all, we use a new thread other than the main thread to listen for the singing event, and we then just send the singing event whenever we heard that, so it's triggered. As you can see, the signals .forever runs indefinitely because we're just listening for such event and send it once we receive that. Then in the third thread, we have the receiving logic. Once we receive the message sent by the thread we used to send the signal, we will just say received SIGINT. Well, the whole logic seems quite straightforward, right? Let's see what will happen if we run it now. So if you just go cargo run, oh, we see an error of missing crate. So this is the first time we see that we are missing some dependencies. So we can fix that by using cargo as terminal hook. That's the package we'll be using that provided the function to listen for the SIGINT event. Let's now run it again. Yeah, it's a bit slower because we're using more dependencies. So let's press Ctrl C. Yeah, I'm just keeping press Ctrl C. So we're getting the SIGINT sent by the signal thread, and we're receiving it in the receiving thread. Right, that's pretty much all for today. So thank you for your watching, and feel free to ask us regarding any questions, but please do try read this code yourself first before you ask, so that we know where exactly you're stuck on. Thank you very much.